All right, so we've already talked about water molecules, and that's we're going to quick review, and then take from water molecules themselves and look at a little bit of their behavior. We're not going to go into everything about water and water molecules, but the one particular topic that we are going to look at is pH. pH is going to be extremely important to cells and to physiology of living things. So it's important to understand the pH scale. Many people are familiar with the pH scale, but I'd say very few people actually understand the pH scale, and most people's concept of it is probably backwards or wrong. So we're going to start off with water. All right. So we've already established that water is made up of oxygen, right? One oxygen. Oxygen has 6 electrons in its outermost shell. Okay. So there's 2 pairs of electrons and there's 2 unpaired electrons. And then we have 2 hydrogens, right? So a hydrogen and a second hydrogen. Each hydrogen has 1 electron. So they share with oxygen. This makes a particular kind of bond. If you remember what type of bond that was, it was a covalent bond. And in particular, it was a polar covalent bond. And this one's going to be the same. So we have 2 polar covalent bonds. So when we look at a water molecule, we may even more simply draw it like this. Draw these 2 lines. These represent the polar covalent bonds here. And now because of this, the oxygen, we said, feels like it's more negatively charged. The hydrogens feel like they're more positively charged. Remember, a hydrogen is 1 proton, 1 electron. Take away its 1 electron, it's just a proton, and so it has a positive charge. When there are multiple water molecules around, and this is a review from a previous lecture, the water molecules will interact. So there will be a particular attraction. The attraction is between the negative and the positive. That's an attraction. And this attraction is what we call a hydrogen bond. Hydrogen bonds are attractions between partially positive hydrogens and partially negative elements of other molecules. And so in this case, that negative element is oxygen from another water molecule. But it could be different types of molecules. It doesn't have to be only water. But we're going to focus on water. And water can do something else. The water molecule, who has the oxygen and hydrogen unevenly sharing electrons, can go a step further. If we once talked about ions and the formation of ions and ionic bonds, and that's when electrons are shared unequally, and the sharing is so unequal that one just steals the electron from the other. So in this case, kind of erase this here. So what would happen if this hydrogen, who was sharing an electron with oxygen, lost the electron completely? Okay. This would now become simply a hydrogen writing backwards and forwards here. Hydrogen ion. Now, this was the partially positive hydrogen. It stays that way. But this oxygen now has gained the electron. It took the electron from this atom, and so now it carries a full negative charge. This is often written like this, OH negative, and that's called a hydroxide ion. So now we have 2 ions, hydroxide ions and hydrogen ions. We're mostly going to be focused on hydrogen ions, but there's something I need to mention. Okay. Water molecules, like this one, who have not dissociated. All right, so dissociation, the water molecule essentially breaks, right, into 2 parts, the hydroxide ion part and the hydrogen ion part. The hydrogen ions who are positively charged are attracted to negative things. So they could be attracted to hydroxide ions and just go back together again. They could also be attracted to here, the partially negative part of another water molecule who has not dissociated. And that does something a little bit different. That creates something unique here. All right, so this is called a hydronium ion. Because in doing so, what's happened is this is a full positive charge, that's been taken up here. So there's then a bond, which is another type of attraction, right, between these two guys. But now you have 3 hydrogens and 1 oxygen. So this H3O plus. So it actually carries the true positive charge of an ion. And we'll usually see, if you look at the book and you look at other sources, you'll look at water dissociating. And then it sometimes shows something funny in the drawings I found in the books. It just shows a hydroxide ion and then hydronium. You're like, well, where did all this extra stuff come from? And this is the explanation. It comes from the hydrogen ion breaks off and then attracts to another water molecule and forms the hydronium ion. However, for simplicity's sake, because we're going to be focused specifically on pH, we're going to focus just on the hydrogen ions, okay? And we're not going to worry too much about the hydronium ions. So I've mentioned them. I want you to know the term. Make sure you understand how they come together. But that's pretty much all we're going to do. At this point, we're going to focus specifically on hydrogen ions and relate it to pH. If you notice, pH itself, right? There's an H, and the H is a capital H. If you do pH and draw pH like this, big P, little h, that's not the pH we're talking about. Okay, that's usually an abbreviation for PhD, which is really pH in philosophy. So it's not the same thing at all. And in science, the particular type of notation that exists or that's used is incredibly important, because there are different notations that mean different things. So it really holds a very different meaning. It's important you actually know that this hydrogen is referring to hydrogen ions. Okay, so in pH, the H of pH is a hydrogen ion. And so that's what we're really getting at. What is pH? So if this erases easily, we'll continue. Otherwise, I'll have to pause. But it's working pretty well. Let me just do this. Clean it right up. Okay. So what is pH? So we don't want this pH. pH with a capital H, right, is really the concentration. So brackets like this refer to concentration. And what's it a concentration of? Well, it's a concentration of hydrogen ions. So that's how we define pH. So if you ask, what is pH? Some people will say, oh, it's how acidic something is, or it's how basic it is. And those things are not false, they're not wrong, but that's not really the true definition that we're after. When we look at pH, we're specifically measuring how many hydrogen ions there are in a particular solution. Where do the hydrogen ions come from in solution? They come from water molecules. Water molecules break apart, right? And you have hydrogen ions and hydroxide ions. What we're going to find is that when they break apart, right, there's going to be a concentration of each of them. And initially, that concentration is equal, right? If you took one water molecule, broke it into 2 halves, you have the same number of each, same number of hydrogen ions as you do hydroxide ions. That would be what we call a neutral pH, which on the pH scale you may know as pH 7. Okay, so pH 7 is neutral because what you have at that point is the same number of hydrogen ions as hydroxide ions. But then you may wonder, but 7? Where does 7 come from? Well, 7 is really referring to the actual concentration of the hydroxide ions themselves. And so now we have to get into something different. The pH scale is sort of a shorthand. Right? What it's really referring to is concentration, and concentration is in molarity. Right? So when we say pH 7, what we really mean is pH 7 is equal to 10 to the negative 7th molar hydrogen ions. Okay, so the concentration of hydrogen ions is 10 to the negative 7th molar, and that's a pH of 7. And so right now you might be like, okay, I don't really follow, but just take that down, right? So that is a true statement. Now when pH is 7 and the hydrogen and hydroxide ion concentrations are equal, well, that means there's something else you already know. That means the concentration of hydroxide ions is also 10 to the negative 7th molar. So you see they're the same. They're the exact same concentration. What is 10 to the negative 7th molar? Well, for this, you also need to know some scientific notation. First is 10 to the negative 7th. That equals 0.1234567, right? 7 decimal places. 1, 2, 3, 4, 5, 6, and then to have a number 1, that would be 7 decimal places we have to move over. That's 10 to the negative 7th. So that's how many hydrogen ions we have in a solution that is pH 7. That's the molar concentration of them. Now, to kind of keep this short and then move on to the next aspect of the topic, we're going to kind of stop here, right, and then break to the next lecture specifically focusing on the pH scale. Okay, so what you should get out of this particular lecture right now is pH has to do with water molecules, and has to do with water molecules breaking apart and putting hydroxide and hydrogen ions into solution. And then when we measure the hydrogen ions, that is the pH. We're going to find that there are other chemicals, the ones that we call acids, right? An acid is going to change the pH of the solution, making it more acidic. It's specifically going to be something that's going to be separate from water, that's going to add hydrogen ions. So this is what we'll also get into, with acids and bases and the general definitions of them and how they actually work. So an acid will be something other than water that's going to add extra hydrogen ions into the solution and then change the overall pH. So they won't be balanced anymore, right? They won't be exactly the same. You might have more hydrogen ions in the solution than hydroxide. And vice versa, those things that we call a base, which we'll get into as well, are going to be things that take away the hydrogen ions, so there'll be more hydroxide. So there's going to be this sort of balance, and that's the thing we get into next. So water molecules breaking apart, that's dissociation. Hydrogen ions, that's what we're focused on, is the concentration of them.